Okay, great. So I will try to give the experimental summary, but this will more be about the experimental highlights. So a few remarks to start. So first of all, thanks a lot to the organizer for the really wonderful conference, and it has really been a pleasure to finally meet everybody again in person, which I'm sure it's also the case for you. And even more on such a special year as the 10th anniversary year of the Higgs boson discovery. I think we really had excellent talks, and I thought the young scientists from they were especially impressive. And we also had really great discussion sessions. Certainly also great thanks to the conveners who have organized those sessions. I certainly cannot make justice for all talks. I think the vast majority of talks is probably worth experimental. So I will need to pick up some topics and highlights that either probably trigger discussion, or probably some of these are controversial, or either that caught my attention. And most likely this is really a biased selection. Also, apologies to all the speakers that I will not properly present in my talk, although I tried hard. The status of Higgs physics today, 10 years after discovery, looking back. So, certainly the main difference is the mere statistical power of the data. We have, also the increasing center of mass energy, more than 30 times more statistics. This was nicely shown, for example, in Tony's talk, where he showed how we see the peak of the Higgs to 4 lepton in the Higgs to 4 lepton channel today. So basically what we saw for the discovery is now really 1/30 of the data, and by now we have really a lot of data that we can use for precision measurements.
That was not 2022, right?
Yeah, I fixed in the news in the slide. Good catch. So also I'd like to start from the fact that we had two truly inspiring historical perspective talks that perspective that Peter Yanni and Jim shared with us. Here's the highlights of the two talks. And it was not only about the talks, but also about the anecdotes and the recollections from those times that they shared. It was really a unique experience, I think. And trying to translate Peter Yanni, I don't have a very good memory, but he said, yeah, these are difficult times today, but you have to fight if you want to reach your objective. And also what Jim said, well, we see obviously not everything will go according to the plans, so you need to be ready for the unexpected and adapt your plans as difficulties come around. I think I can say probably on behalf of everybody of us, and maybe especially those who came relatively late in the game. Like, for example, I started working on Atlas, it was just a few years before the start of data trading, which means that basically everything, the design, the construction was basically done, except for minor points, that we are really deeply indebted to Peter and Jim's leadership, who made two marvelous detectors such as Atlas and CMS become a reality. And also, I think we should remember these words when we will be fighting for the next collider. This time, we probably should also decide exactly what next collider to focus on before fighting for it. So now I will go through some highlights of this conference, and they will be a little bit scattered because by now the picture is relatively complete, and now we are completing, at least from the full run to date, and we are completing this picture in some of the points. And so, for example, let's start from Higgs to diphoton, taking as an example. We had the presentation from Tony, for example, about the results in Higgs to gamma-gamma. Here we have the signal strength in various production modes. And one thing you realize, and this is a thing that also Fabio mentioned, is that some of these, the ones which we measure with highest precision, and this is even more the case for the combination, start really to be significantly impacted by theory uncertainty, despite the excellent progress of the theory in the last years. And if you look more closely, Tony showed, for example, a table with the systematics, you also realize in some cases the uncertainties are higher than the uncertainty on the inclusive cross-section, which means that this is probably due to the way the analyses are run. So acceptance effect combined with effect coefficient, etc., actually can enhance these uncertainties. So at some point we might need to start optimizing analysis to minimize theory errors, and I'm sure some theorists in the room will already may start screaming about this, because of course this is something that you have to do really very careful, and again we'll have to do it in collaboration with the theorists to make sure that what we optimize over is something solid and not just our current understanding of things. We have also seen many more differential distributions being coming around, I mean, both in CMS and Ruggiero showed some for Atlas. This is again from Higgs to gamma gamma, so differential measurements in PTX and jet, and PTX and then YH. And we also discussed that from a theoretical point of view, we need to be quite careful about the theory uncertainties at high PT. And there's still some work being ongoing in the LHC working group about that to refine such uncertainties. Also, clearly, and this is true for most analysis, Atlas and CMS analysis went already through a huge amount of optimization, right? And still, it's impressive to see that every iteration brings improvements beyond statistics. And for example, here, just make one example. By now, we routinely use machine learning, either BDTs, deep neural networks, etc., to improve the separation of signal and background and categorize events in different categories, different S over B. And one thing which was done in Atlas is, for example, to use the d-optimality. So you do not only characterize events, but you actually optimize the exact cuts of the BDT based on directly iteratively optimizing the final covariance matrix, so minimizing basically directly the measurement uncertainty. So this is very nice because it basically makes a multi-dimensional problem much more easy to deal with. But this is just an example. There's a huge amount of problem across the different analysis. We had a presentation by Sidran about an updated Atlas mass measurement. I will maybe not go into the details, but there's a lot of work in trying to pin down uncertainties further, for example, systematic uncertainties. And the thing I wanted to mention is that, for example, this work led to reduce the muon momentum scale by 50%. For now, it doesn't really pay off a lot because the statistical uncertainties is still pretty large, but for the future, this is a key element to ultimately reduce the measurement uncertainty. So today in Atlas, this measurement along full run 2, we are at 0.14% uncertainty. The state of the art from CMS is 0.11%. And here, this has still potential because this is only on partial run 2 plus run 1. So both experiments will need to complete this analysis, which are very complex. And the main work which is being done is in exactly understanding in detail such systematic uncertainties and muon and electron photon calibrations. So let me come to the case for fermions, where we had quite some update at this conference. It was also TDH production. So we had a new result from CMS. So the inclusive strength is 0.6 with uncertainty around 0.2. So it's relatively low. The observed significance is 3.3 sigma, so going a bit down from the observation. So you see that there have been already several cross-checks performed by the CMS analysts. So, for example, a sort of digest environment mass-based analysis used mass-correlated deep neural network, and this is what you see here. And you see that the signal is indeed lower than expected, so it's a factor of 3 lower than 1. But this is sort of compatible with the more aggressive nominal deep neural network analysis. So it's sort of ensures that there's not a problem with that. They also did a measurement of the dye boson peak, so Z to BB bar, and they found the results compatible with 1. So furthermore, Christina also, let me state that why does this actually matter? Well, if you think about putting this into the combination, we also had a discussion already in this days about that since the Higgs BB bar decay dominates the total Higgs field, it eventually will rescale up by quite a bit all the Higgs coupling. So this is something which matters. And so there are many cross-checks that the team has already done. So I mentioned the dye boson. One has also mentioned that the same targets were used as in the previous results. And what is also nice, the boosted region was added. If you look at the result a little bit more carefully versus various different regions, you can see a slight trend versus PT. They are not ordered, but if you look, the ones with the category with lower PT tend to have a lower result than the one with higher PT. If you compare this with the Atlas result, this is not what we see in Atlas. To be honest, in Atlas, maybe we see even too much agreement with the normal. But this is what we see, and I suspect this is what CMS sees for now. And maybe the only thing to learn here for sure is that there will be more cross-checks ongoing. And the second is the combination of Atlas and CMS will take surely time. And so, in fact, one thing that people have wanted is to start producing common samples for the systematic, which may be the only way to really evaluate the correlation between the theory and service once the rest is sorted out, and which may take time. Okay, on the Atlas side, the latest result is the combination of resolved and boosted. So you see here, this is the resolved analysis, and this is the boosted, where the Higgs decays into one merged jet with the two B subjects. We do something simpler for now in Atlas. We just remove the overlap by considering the boosted analysis only for PTV above 400 GeV. So in practice, it does touch on the overall cross-section, but it helps improve the measurement IPT. And you can see this here because now basically there's one additional bin for PTV above 400 GeV, and this helps quite a bit in constraining the Wilson coefficients in the EFT. Let me also mention that LHCb has been now for several years entering the game of producing Higgs physics measurements. The main limitation is clearly the limited acceptance, which is signal efficiency, but also the non-hermetic coverage, which means you get a lot of background just because you are missing things somewhere else, like TD bar. But I think on the good side, you have access to a complementary region of phase space, which does in some kind of access, but we don't have a tracker in that forward region for most of it. And they have excellent vertex reconstruction and PID that potentially can be used, for example, in B-tagging. As far as I understood, the B-tagging performance for now is comparable to what Atlas and CMS have with state-of-the-art taggers, but I think there's quite a disparity in terms of techniques that are currently used in the two cases, so there's quite some potential to improve that. Currently, the limits on the U-kappa coupling based on the full run 1 of the LHCb is that the coupling scale is smaller than 6, and for charm smaller than 80. But there's some potential set to improve this towards the future. So, in terms of Higgs to tau tau, we've seen the results presented by both Atlas, like Giuseppe, and Priscilla for CMS. I think what is very interesting, and especially in the Higgs to tau tau case, which has a relatively large ranking ratio, is that you can improve the precision of the measurement of PT Higgs in the region of IPT. We see this in case of Atlas for SCXS, this is about 300 GeV. And for CMS, you see it in the first and pretty nice differential measurements in the fiduciary region, which they did. And you see now this measurement IPT. Of course, this is interesting because if you have a deviation that you do to the standard model physics, as highlighted several times by Giacinto et al. And many theorists, you may see a deviation first in these bits. However, as you can see, for now, the data points, they align pretty well with the prediction, despite all the limitations of the prediction IPT. Okay, complementary way to probe the Higgs coupling to fermions, so TTH Higgs to multi-leptons. Here, remember that CMS, the results are updated to the full run 2, but Atlas, it's still only partial run 2. I think, actually, it's wrong, sorry, it's, I think, 80. I know. And this is due to the fact that there's some problem modeling TD bar correctly. Both Atlas and CMS see that the cross-section is underestimated by Monte Carlo. And what Atlas does in addition is modeling in the differential prediction for TTW and charge asymmetry. There's a strong effort by the whole community in the Higgs working group to improve the description. So there's actually quite some work ongoing there. In this case, common background Monte Carlos have already been produced and compared between Atlas and CMS, which I think is really great towards the future. Atlas started a program around measurements in these channels. So it was our first measurement at charge asymmetry in TW events. This is what Brandon showed, the charge asymmetry is defined here. For now, this measurement here, with all experimental uncertainty, etc., is compatible with the prediction. So there's no deviations in here, but this measurement program will contribute in other respects. So let me come to the Higgs combination. So first of all, I saw the plot from Alina David's plot because it shows nicely that by now almost all product combinations of production modes and decay modes are covered in the combination. In fact, the point of view changed a little bit. By now, we don't ask ourselves what did make it into the combinations, but I think what we ask is what did not make it. And so, for example, for CMS, and this tables were shown in the combination section, So the main missing channels by Bob and Fabio, so the main missing channels for CMS where VH is to be big with full run 2, but we just saw this new result, we just didn't make it yet to the combination. And TTH Higgs to be big with full run 2. And on the other side, we saw, I think VH Higgs to W with full run 2 is still missing. And then the TTH Higgs to multilateral we just discussed, because I mean, TDW measurement is currently being performed modeling. And okay, some additional modes for Higgs to invisible where CMS has been really very, very quick. So I think by now you can almost ask the question, most cases, are there any good reasons why CMS or Atlas may be late on these channels? I think we've seen some examples here already. But things, in general, things are, I mean, the picture is getting complete and soon we have the full combination. So in terms of overall single strength, so here you see, and this is from CMS from Fabio, you see an incredible progression since the discovery, 23% uncertainty down to now 6%. The final numbers and uncertainty is very, it's compatible with 1 and very close in terms of uncertainty also for Atlas, 6%. So both Atlas and CMS basically measure 1 with an uncertainty of 6%, which is really remarkable. And the 6%, I mean. And also the experimental and theory systematic errors went down by factor of 2 since run 2. Since run 1. So in terms of production decay mode, by now we have established most of the production modes and most of the decay modes, and we start to access the rare decay modes. Here there's new, but there are also Z gamma. Actually, it's interesting that both Atlas and CMS see a first hint of Z gamma, 2.7 sigma, 2.2 sigma, compared with the standard moment expectation at 1 to 1.5 sigma level, but slightly high. So we'll see in the future what happens to that. So by now, both Atlas and CMS have established measurements for the simplified template cross-section. It's a convenient way to basically do all differential measurements in the various production modes. And here there's a nice result, which a nice display of results which Atlas published in Nature for the anniversary. And yeah, you see that, I mean, the combination is really what brings a huge amount of power into this. For example, here there's CPH, and you see here there's a complementarity really of Higgs to gamma gamma, multilepton, it all contributes to determining this differential cross-section versus PT Higgs. So I think that's quite impressive, especially compared with respect to a few years ago. So here, just an update of this is partly showed as well, so I can go quick. This is the update on the kappa, on the Higgs couplings for both CMS and Atlas, as shown by Fabio and Paolo. And you see that we are reaching precision between 5, 8, and 10%. And it's also very interesting that on the branching ratio for invisible and detective decay, we are now at the level of 10 to 15%. But I'll say a little bit more later about this. One thing which we should remind ourselves in this conference, sometimes it was seemed to be forgotten, that we cannot directly measure the total width of the LHC. So we need an additional assumption to determine the branching ratio and detector. So for example, we need to impose kind of the possibility, the KV, W, or Z to be below 1. So it's a sort of unitarity constraint. Alternative is to use, for example, the off-shell part of the Higgs cross-section, something that, for example, Atlas has done for the final 1-1 combination, which I guess Atlas CMS could also take again for the future. Okay, yes, so I will actually skip the interpretation because Fabio has shown that quite extensively, but I think the latest results are also really nice and unfortunately show no deviation from the standard model either. And so I will move to searches for BSM, to more explicit searches for BSM. And so first, the search for additional scalar bosons. So there's a whole suite of new results by Atlas and CMS, so I cannot certainly cover it in a summary to give a flavor. So this is event for CMS and Chaton for Atlas. And so here, of course, what you focus on are the excessivity, it's the usual thing. So here there are 2 from CMS, 1 from Atlas. There was actually quite some discussion about this one, because 3.8 sigma local and 2.8 sigma global. But let's say, but we have to take this with a grain of salt. We had some discussion, and also Bob led this discussion, that the look elsewhere effect is like it's defined for a single channel, right? So if you look at more globally, we have to wait a little bit more before we got too excited. And yes, and certainly more data in these channels as well as another will tell us if there's anything real behind these excesses. So let me come to search for rare and BSM decays. So these are just some new results. I'll focus on those. So Giacinto presented results for Higgs to photon, dark photon in Atlas, which is basically as a the electron plus photon plus missing ET final state. Searches for dark photon between 0 and 40 GeV. They find nothing and could set a limit on the branching ratio. Maxime showed an interesting results with the alpha Higgs going to two scalars and 4 photons. What is interesting here is that, as also in other cases, Atlas and CMS are developing new dedicated reconstruction techniques that are aimed at very specific final states. For example, here there's the analysis made possible the NN-based reconstruction of merged photons, and this was actually published separately. In Atlas, for example, we had the reconstruction of merged electrons, which made, for example, the first evidence of EE gamma possible, for example. So in this case, they managed through this technique to probe masses of the air as small as 1.2 GeV, and here there's a plot of the data versus Monte Carlo comparison of the invariant mass of this A from these merged photons, and you see the nice agreement between the data and the prediction, and here the models or the simulation of for various types of signal. This is a limit plot, the 95% confidence limit against the mass of this intermediate A particle, and you see that unfortunately there's no significant excess, and they move to set limits on the branching ratio at the level of 1 to 3 per mil. There was an update on, quite some update on searches on Higgs invisible from CMS by Olivier. Just a reminder that the most sensitive mode for Higgs invisible is certainly vector boson fusion. And for example, it was nice to see that here also there's improvements going on. For example, the CMS uses an updated combination of VBF and missing ET triggers. The VBF triggers basically allow to reduce the threshold for the missing ET, and so increase signal acceptance, as well as improve the background estimates, for example, including the gamma plus jet into the estimate. And the limit here is, there's a slight excess, but the expected limit is around 10%. And it's actually very close to also what is seen in Atlas, a sign that we are converging on getting this analysis as optimized as basically the detector can let them to do. So, and then, however, CMS is also working on very hard on the other production modes which are less sensitive. And so, for example, there was an updated result of BH hadronic and TBH hadronic. These are less sensitive, but they are a lot of work because they're also pretty challenging. But the good thing is that if you combine them all, you can gain a little bit. So, for example, here at the end, you can go from the 10% expected to 8%, which is quite a significant improvement in the end. So it is definitely work that pays off, and also actually Atlas is still working on a few, but also has already several that made it into the combination. Okay, so then we had in terms of searches for rare decays, we had also Antonio presenting new results, Atlas results on flavor lepton violating decays of the Higgs to E tau or mu tau, which was just released. Here are the plots for the limits of the different channels, but the main point is that the limits on the branching ratio for being in the standard model is at the level of 0.2%, which is similar to, I think, or it's not there, I will check. It is similar to the comparable limits from CMS. So, let me comment that one hot topic of this conference, which was the city structure of the Higgs couplings, where there's a lot of activity, and a reminder that the set of conditions to explain biogenesis in the evolution of our universe is that you need to have C and CP violation as necessary but not sufficient conditions. And in particular, as Marcella has reminded us in her talk, the CP violation in the CKM sector and maybe even in the neutrino sector is too small to explain it. And in the following, I'll just focus on the coupling to fermions. So the CB violation, the coupling to fermions can happen at 3 levels. So you have now a CB even augmented by a CB odd component. and you can build an angle by the ratio of these two couplings, and this angle basically represents the CP structure of the coupling. And so it turns out, and this is something which started only recently, several years ago. Initially, I mean, this was thought to be a really challenging measurements before, is that one can really measure the CP in the decay of the Higgs to tau leptons by basically using tau substructure information. So the principle is simple. Due to spin correlation, you have to measure the angle between the decay planes of the taus, and there are several ways depending on which decay mode you consider. The key asset is to have a tau reconstruction which allows you to determine the direction position of the charge, but also neutral particles, which is something which was really actively improved both in ATLAS and in CMS. And at the end, what you get, if you look at this angle, you get a sinusoidal behavior, which is basically shifted by this CP angle. So both CMS and ATLAS did the measurements trying to maximize the sensitivity to this angle. And you see that, so this is basically this angle sensitive to CP, with the right signs, depending on the decay mode, etc., being in means of the neural network or UDT, which give different signal background ratio. So the last is the most pure, and you see the difference between the two types of hypotheses here, CP even CP odd. By using that, you can measure this angle, and you get here the 9 plus minus 16 degrees in CMS and -1 plus minus 19 degrees in ATLAS. To be honest, these numbers are incredibly close in terms of sensitivity, which is again a sign that both experimental collaborations have worked pretty hard to optimize this analysis. Last, you can also measure the CP of the Higgs coupling to quarks in top quarks in the TTH production, and here there are several examples. So, for example, Andrea Porciana showed Higgs to gamma gamma ZZ, Ricardo Higgs to gamma gamma, and then there was a nice talk by Neelam on trying to do the same in Higgs to dB bar. So for the other two, basically ATLAS and CMS are able to exclude CP odd, especially more than the 3 sigma level. And instead for Higgs to dB, this is a nice addition, but what was done, for example, to define new CP sensitive variables based on the TTH system reconstructed in the Higgs to dB final state. But this is a really challenging analysis. In fact, it turns out that the TTBBB background, and particularly for measuring CP, is very difficult to control, and some of the uncertainties turn out to be pretty large. However, it still gives sort of a little bit of an improvement to when combined with the other channels. Okay, let me come to the Higgs coupling, for which we had quite some discussion in this conference. So, in terms of motivation, here there's a nice picture which was planned in Gavin Salam Nature article for the anniversary. I mean, the main idea is that we know what is happening basically around here, because we found the Higgs, we've measured the mass, but as soon as we go a little bit away from this, we basically don't know yet whether what is realized is the standard model potential or something different. And the shape of this potential, as we heard now several times, also today and by Marcella, is that we want to understand whether electroweak biogenesis may explain matter-antimatter asymmetry in our universe, and for that, one crucial piece of information is the shape of this potential. In ATLAS and CMS, the main three search modes are one Higgs PV, the other either to dB tau tau gamma gamma, and latest results have been presented by both ATLAS and CMS. And you see that in the end, for now, the limit on the cross section of the Higgs is around 2.5 or 3.5, but the expected sensitivities are relatively close. In the next slide, we will focus on a few young scientists talks that actually show very nicely what impressive improvement has been achieved since the partial run 2 data set in some of these channels. And it happens these were all from CMS. So this for BB tau tau, there was a factor of 5 improvement as well as for B, and the increase in data set was a factor of 4. So most of the improvement was due to the improved analysis techniques. And ATLAS presented a nice combination of single Higgs with di-Higgs. So let me go to Valaire's talk on Higgs, di-Higgs to dB tau tau. So what has been improved here is a new trigger strategy, a new deep neural network to separate signal and background better, a new flavor and how tagging based on the deep neural network versions. As said, there's a factor of 2.5 improvement beyond statistics due to these improvements. And here there's the new result, which is the limit on sigma over sigma standard model around 5, which is actually now pretty comparable to the result by Atlas, while before the Atlas result was clearly had clearly an edge. Actually, you see now the expected is even better in CMS. So for the Higgs 2,4b analysis, a really significant improvement has been achieved in the boosted case. Here, the new particle net tagger is used to separate merge threads from X2DB from QCD. Parkinson mentioned this also in the context of Higgs to CT bar, which we didn't discuss a lot in this conference. But so it's a graph neural network based on low-level particle flow and detailed information. A new method was developed to avoid the distortion of the mass spectrum. But maybe one thing which we should highlight here, and it's true for many of these deep learning techniques, it is extremely challenging to really calibrate them. And we also discussed pin down what the uncertainty is. So for example, here you can see this very clearly and appreciate very clearly if you read through the document, through this first document, highlighting the features of this calibration. So here, so for this analysis, what was done, instead of fitting the final n the Higgs mass, the final spectrum that they fit is the mass of the second merged jet. And you can see here that there's a slight excess. This is 3 times the signal which they expect. But you see, even so, you see that the level of signal of background achieved through this analysis, being a Higgs analysis, is really impressive. Even if you scale the red down by 1/3, it's still for a Higgs signal, it's pretty impressive. So the result, in fact, is that they expect now the exclusion went down, expected to 5, which is too low, and they see a slight excess, so they can exclude a little bit less. So Atlas and in particular Arcade present an update on the combination of single Higgs and double Higgs in terms of constraining the trilinear coupling of the Higgs. This dependence, which is used by both Atlas and CMS, of the cross-section SCXS spins on the trilinear coupling has been derived now in the LSC Higgs working group, and is used by both collaborations. I mean, one thing which is a bit striking. So this is a really nice way to integrate single Higgs and double Higgs measurements in the most correct way. One thing which is sort of interesting is that the improvement from adding single Higgs is not actually that large. And the reason, turns out, we had also a discussion on Mattermost of this, is that really the single Higgs constraint is dominated by the rate measurement in signal Higgs. The modifications of the self-coupling are really small, and these are by now partially already theoretically and theoretically limited. So it's not clear whether we can improve there a lot towards the future. It's also nice to see that CMS also did the first measurement of or constraint on phi lambda using single Higgs. And you can see also here that the limits are quite a bit worse than the one from direct production. Towards the future, Higgs will dominate even more because it's clearly statistically limited. Okay, we need to skip this, but Fabio mentioned it quite in some detail, so that's very nice. And I will skip this, and I will instead move to the prospects for the future, which we have discussed today. So this is the skeleton towards Halloumi SC. Yeah, I don't have the stretched version of Fabio, but still, I try to highlight how much it is from today. Today to it's 20 years from now. So but at the same time, it seems like a long time. But of course, building the next collider may well require more than 20 years. So maybe, yeah, I think someone like Jim said that maybe all the numbers we have for now are unrealistic. And with Peter Yannis' work, we need to fight for it, right, to get it funded. So the projection, so the first, it's almost already reality. Halloumi is almost here. So what can we do there? Well, we can improve quite a bit the measurement of the couplings to single Higgs. We said 1.5 to 4%. And we can do actually even better, probably if our theory colleagues help us further in this direction. But the other point, which was made earlier today, is also a very good one. We need to exploit, I think, Carnegie, that we need to exploit more differential measurements in the hyper details, etc. We have done a bit, not a lot for now for this projections. For the trilinear Higgs coupling, we will have first bounce on the Higgs coupling. I haven't put a number here because I think that things are really improving while we speak. So any number will be outdated by the end of this conference. And this is what Liza nicely has shown here. So beyond high luminance LHC, we just said it's 20 years from, but okay, many possible colliders. And so I think, my opinion, the community needs to converge on one or maybe two, but probably one option. The lepton collider, we had a talk by Gautier on lepton colliders. It provides lower cross-section, but as we know, a very clean environment and excellent resolution in particle ID. Done my master thesis on Barbar, and later I have a little bit experience of what it means to work on the plus and minus collider. It's different, it's really a different world. Surely this is much higher energy, so it's different, but still. Okay, I quote this from the European Strategy Update in 2020, but I guess by now discussions are still further ongoing. There are many options available also for a lepton collider, as was here nicely shown in this plot of luminosity versus effective center of mass energy. So one has to really pin down what one really wants. Prospects at future collider, where we know that we can have large improvements everywhere except where, from a lepton collider, for example, except where statistical uncertainty dominates, which is maybe only probably Z gamma and muons. So, and also, I want to state also that it's not only about quantitative improvements. No, we actually make some conceptual assumption when we make this plot, absolute coupling. So when you have an electron-positron collider, or you also you have a model independent access to the coupling because you can probe the production sort of independently from the decay, which is really a big plus. And this is not it's not highlighted by this plot. And actually, Gautier clarified this, said this very clearly. So we have an update. We have actually updated protection from SNOMAS. This is a really nice result of SNOMAS. So this is for the trilinear coupling. So it's missing here. So here, actually, for high luminance, 50% is spot, and this is what you can do with the various different options. In general, for the trilinear coupling, as you would expect, high energy is favored. And at E plus, E minus, because of how precisely you can measure single Higgs rates, and also, I should also add, because of how precisely you can compute higher order corrections, right, from the theory perspective, it becomes feasible to constrain K lambda precisely from single Higgs measurement. Okay, and this is highlighted already. Let me also highlight that the muon collider has entered the game, at least it has been studied, I think, much more carefully and deeply during the SNOMAS exercise. So I think we'll need in the next probably months or years to understand a little bit better how that fits into the global picture. I've seen it's already part of the strategy also of ECFA, it's highlighted towards the end. But clearly there are a lot of options still highlighted there. Okay, and last, the RD roadmap towards the future. So Carl highlighted what is now already an official document of ECFA and was presented to the CERN Council in December of last year and seeks approval by the end of this year. The roadmap is a really detailed roadmap, which includes RD for both accelerators and detectors. And so there are still quite a few options on the table, but maybe this makes sense at this stage, right? Where there's some significant RD, for example, to even understand whether a muon collider is feasible at all. But even for the same can be said for some of these other options. The SNOMAS process is just ending, which is, and Menachi gives a great clear picture of where we are in that term. And P5 will now meet and define the priority, at least on the US side. And there are some proposals that emerge to host either the 3C copper-cooled collider or the muon collider in the US. CQ. Thank you. It's easier. Yeah. And you can see them appearing here. With timescale that perhaps we discussed are slightly optimistic, but they're really interesting. It's very interesting that the US, I think, is at least thinking about the possibility to host a collider, and it's even considering hosting the AEC. So we'll have to see what the decision is, and then how that will fit into the into the more global picture. Concluding, I think we have come really a long way since the Higgs boson discovery. And yes, since Fabio showed a CMS picture, I had to show here another picture, of course. It's an impressive suite of results which was really presented at Higgs Hunting, and I tried to go through the main results, but of course I didn't make justice to all the results presented. But I think the key, I mean, what we've seen and what was most interesting is really to see innovations in almost all respects, and analysis that routinely exceed the expectation. I mean, those innovations are usually young or also sometimes less young people who think hard about how to improve analysis, what could be interesting, do R&D, and then plug it into the analysis. And we definitely need that. It's one of the most interesting and most important aspects of our community. At the same time, our community is working or actively engaged in preparing for the future. Well, Halong LSC will be ready in a few years, and many of us are working on making it happen. But at the same time, we shouldn't forget about the discussion and the R&D activities ongoing to define the next collider, because such endeavors take a huge amount of time to prepare and then pursue. And I guess with this, I've seen this program for Louis and Nicola, the organizers, that there were a few suggestions the past years to change the name, like Higgs Hunting or Still Hunting, etc. So I thought, well, because we clearly reached an era where we have a precision measurements, but I thought the session that Liza sort of organized on the Higgs and the discussion showed that perhaps there are still reasons why we're still at the 100%. So probably the name, okay. And with that, I close the talk and just thank
Thanks, Giacinto. Questions to the last talk?
I wonder about the TTW representation by Monte Carlo. Is that just a Monte Carlo problem, or there is an excess in
This was exactly the reason for somebody to do a first charge asymmetry measurement, because you could think that there's some. I mean, it's hard to disentangle the two if you're not sure about your prediction, of course, but still. But for that first measurement gave no discrepancy. I must also say that, of course, when you do such an analysis, okay, I'm not going to do this. At some point, so you do your analysis, you fix everything, and then you unblind. And then at that point, you have a very well-defined statistical procedure. At the moment you start to instead verify additional distribution, etc., it's a very delicate problem because, of course, you have to really be careful in terms of interpreting what you see. It's really hard to actually interpret what you see a possible excess in a certain region of phase space as a real excess. So it's much better than to go back, find yourself, define what you exactly want to see, and such as it's statistically sound, and then you look back and say, is such an excess or deviation really significant? I think that is what was done with this measurement, and basically this measurement tells us that things are okay.
But the measurement is just an asymmetry, right?
Yeah.
But not the total rate, the total
rate. Yes.
But and the symmetry is the.
So the question there is it just the I mean, sometimes we know that total rates are not so very well predicted, but at the same time, whether we expect that the shapes are relatively well predicted. But
also the question. Okay, no, I agree. No, I'm not arguing with you, but the symmetry still has large errors and I mean,
One last question.
You showed a little table towards the end of how well you measure triple Higgs.
Yes.
Where at the HLOC, I thought I saw 50%.
Yeah, right. This is from the Snowmaster exercise.
Now, maybe I misunderstood something that was said a little earlier today, but I thought the numbers, it was statements, we think we can get up to 4.6 sigma and maybe to 5 sigma.
At high luminosity?
Ash production.
On the observational
Maybe
observation.
Yeah, so sorry, there are two different questions here. One is how sensitive we are to the standard model cross-section. Right?
Okay.
So whether if the standard model is revised measure, how significant will be the observation that we expect. So can we see a direct signal corresponding to the standard model?
Okay.
But another question is how precisely can we measure the trilinear Higgs coupling? And because now the destructive interference between the two diagrams, so that's much harder. And so there, it's about 50%. I didn't actually give a number because I said this number is really changing
Right.
by the day, but
So
it's approximately
the 4 to 5 sigma was
on the Higgs.
just the dihedral signal
Yes.
itself.
Yes.
Thank you.
Okay, one more round, we still have 2 minutes.
I have a question on Higgs to 1000p on your slide 34.
Yes.
So you have Atlas and CMS side by side, and what I found very striking on there that makes me wonder is the CMS prediction for the background is like extremely flat. So how are they estimated here? Like why do I not see bin-to-bin fluctuations in the templates?
I mean, CMS clearly, but they basically use, they know that the background has some symmetry, in the case it's that, and they use this information to constrain the template. But probably we have a CMS.
Exactly. So we use the background, we use the symmetrization or flattening, or basically estimating, basically to reduce the background multiplier fluctuation in the bin.
And since you know what we talk about that background is, it makes sense to use it as something to reduce your fluctuation.
Okay, thanks.
Okay, then let's take the check.